Here is a high availability concept for a medieval castle. Let's take a look at some of the concepts here. In terms of a secure castle, it would be designed for resilience. This means that there could be fortified walls. So, this means that even if one of the walls is temporarily compromised, it's fortified by other means so that it won't just topple right over. And an escape tunnel as well as a really good way to prevent isolation. So, let's say the castle was under siege, there could be a secret escape tunnel that allow people to get provisions or maybe go in a boat and go to some other location, then come back. Also, a deep well could be a way to make the castle highly available because the deep well would be able to provide water even though the castle was under siege. So, this is really a concept here of thinking ahead of time when you're building a medieval castle. Like, what are some of the things that come up, and how do I make sure that the castle is always available and it doesn't collapse from an attack or a siege? Can I get out? Can I also continue to thrive inside of the castle? So, a computer system is very similar in that it is going to design a system that is going to really be able to respond to high availability events. So, this could be multiple internet links to prevent connectivity loss, a redundant power supply for shutdowns, maybe even a battery backup system, solar power, mirrored servers could ensure continuity if one fails. And also, geographic distribution of infrastructure would also be a way to limit the localized outages, and load balancers would be spread across the different resources. And then when there's a scaling issue, it could elastically accommodate this spike in demand. So achieving high availability really means thinking about the fact that failure will occur, either in the case of the castle or with a computer system. So you don't want a single point of failure. You would eliminate them. And you also want to eliminate downtime because you have some kind of failover capability. So, for example, the tunnel, the downtime would be that if you can't get out, you could really have some issues. So you would design the system knowing that you could escape. In terms of the backup power generator ticking in, or a replicated database, or anything like that, this is a similar concept in the computer world. So, a proper high availability design would be able to weather the storm and have a safety net. And with a sound architecture, your system would operate at a castle like security level and a castle like level of resilience. Here we have a homophonic cipher, and this Rust code implements a homophonic cipher encryption by generating a random mapping of characters to multiple homophone substitutes. It prints the plain text, ciphertext, and mapping. So we have a good idea of exactly what's happening here. And a cipher is a method of encrypting text by substituting letters or symbols for other letters or symbols based on a scheme or algorithm. This is really common for royalty, back in, let's say, the 1500s. Mary, Queen of Scots, is famous for using ciphers, and there's a very interesting story about that as well. Ciphers aim to make a message unreadable to anyone except the intended recipient with the secret knowledge of how to decrypt it. This homophonic cipher is very interesting because it creates a more secure type of encryption than a simple one where you're just substituting characters to multiple homophones, letters that sound alike. This is more ambiguous because the ciphertext is harder to crack through frequency analysis because it could be one of many different letters. And so, in summary, this is a way of demonstrating how to encrypt text in the old days by using the Rust language. So, if we go through here and we look at the RAM here, we look at HashMap, really that's all we need. And we build out a function called homophonic cipher. Inside takes plain text. It's going to return, though, this hash map uh, in a vector as well. So if we go through here and we look at the random here, we look at alphabet, we look at ciphertext, and now this is pretty clever, is that all you have to do is say A to Z, and we're able to collect those into a vector, and then we go ahead and we map those all together. And then what happens is essentially we figure out some random substitutes for those particular letters in the alphabet. And then we go through here and we put it all together and we push that out and we even print out the plain text, the ciphertext, and the mapping. And then at the very end, it actually goes through and it returns back those items. Finally, all we have to do is actually run the main function and put in some string that gives us the cipher. So if we go through here and we write cargo run, this is going to go through a build it. And then we can see here that the plain text was the quick brown fox jumps over the lazy dog. The ciphertext is all gibberish, but we can see here that there's mappings here where each of these letters that is substituted here has, basically different pairs that it could be mapped exactly to that particular letter. So it makes it a little bit more difficult because it's not necessarily a one-to-one mapping, et cetera. It's actually one of many different mappings. So this is a great way to play around with ciphers and encryption is to use Rust. It's prescript word. Also, if we go through here and we look at the documentation, we can even see a little bit more information, and it generates a list of random homophones for each lowercase letter in the English alphabet and maps those. And you can see here's an example of what's happening. And you can see that the mapping T is part of the homophonic cipher mapping from plaintext characters to their cipher characters. And in this exact example here, the plaintext character T can be represented by either a Q, an A, or a V. So this makes it more ambiguous about what is actually happening, a little bit more difficult to do frequency analysis because there's some letters that show up a lot more frequently, and so that makes it harder to break. Comparing this to, let's say, something really simple where you just substitute an A for a Z or a B for an F or something like that. All right, join me on a journey here to the clandestine world of secret messages. I'm going to be your guide as we encrypt a plain text message and then render it unreadable to people that want to intercept it. But don't worry, the secret shift value is very clear here, and I can reverse the cipher and reveal the original text again. So what we're going to do is look at the encrypt function because it's what performs the mysterious art of substitution, and it's going to shift each letter to hide the content. And the result is going to be incomprehensible without knowledge of cipher. So let's go ahead and take a look at how this works. So first step here, we have the use Caesar cipher decrypt, use Caesar cipher encrypt. Let's go to the lib directory, which is a common place in Rust for you to build out your logic. And this thing here has an encrypt, and it's pretty simple. It takes some text and it takes a shift value. So all the shift is what is going to be the letter substitute, right? So if you started with A and you shifted to two letters, it would be C. And if it would be three, it would be D. So in this case, what we're going to do is we're going to take in the string. We're going to say for all of the characters in the text, do a little bit of pre-processing, lowercase it, but basically shift it according to whatever shift value is here. Likewise, to decrypt, you just shift it back into the other direction. Now, if we go to the main function here, we can see how it works in action is there's a plain text value that's hard-coded in here. There's a shift value that's hard-coded, and then you are able to both encrypt it and decrypt it according to this Caesar cipher. So let's go ahead and cd into this directory first. I'm going to go into the Caesar cipher directory, type in cargo run. Now we can see here that the quick brown fox jumps over the lazy dog. It has been shifted, right? So if we know that there's three different letters difference, is going to be TU, VW, right? And so we can see here that you could, in theory, do this by hand if you knew what the shift value was and fairly quickly, undecipher or remove the complexity of what's happening inside of the original Caesar cipher. But in this case, if we decrypt it again, you can see what the value is. So this is a great proof of concept to start to dive into ciphers. And of course, with Rust, it's pretty straightforward to build these things here, just a little bit of code. And this is a good example that I would recommend to play around with.